Alrighty. Hello, everyone. My name is Spencer, and I'm the team lead of Team Aegis. So we are a team of students, both undergrad and graduates from USC and UC Berkeley. So for this year, we are a returning team of 2 years, and we do have quite the large roster, 19 folks. But for this presentation, my co-presenters Bazam and Zubam will be giving us a rundown of Senva 2, which is our software package, also known as Surface Exploration Navigation Visual Assistant. So without further ado, let's dive right into our product reel. I love that. Special thanks to our marketing head, Stanley, for putting that all together. And yes, I did change hairstyles halfway through development because, wow, it is quite the pain with long hair developing on the HoloLens. But anyway, that's all nice and all. But what exactly is Senva? So to better illustrate the software package that we have created, here is a ConOps diagram of basically combining three different nascent technologies: augmented reality or or AR, natural language processing or NLP, and computer vision CV into a cohesive software package that guides astronauts from egress through navigation, spectroscopy, rover commands, and more. And the goal here is really to reduce the amount of cognitive load that is placed upon astronauts during EVAs while improving their safety by improving their situational awareness.
We'd like to start off with a key feature that makes our project very distinguishable. Traveler, our built in house, off cloud, server based AI companion. Connected to the HoloLens always without any internet. From speech recognition to natural language understanding to text to speech with computer vision, we fuel astronauts' capabilities to with the traveler's task-oriented dialogue agent along with gaze-based input, reducing the cognitive load and facilitating the computational complexity and weight of the helmet. Traveler supports several tasks, including reading out information and manipulating the UI, and assisting in defined procedural scenarios such as umbilical interface assembly of egress procedure, as well as lunar sample tagging using object detection and holographic highlighting.
Now let's talk about navigation. So we don't have Google Maps or Apple Maps on Moon, do we? And we don't want our astronauts to get lost in space. So, but our customizable pathfinder is to the rescue. So we utilize A star algorithm to find an optimal path from point A to point B, and in real time, and represent those waypoints in real world space with directional orientation. As you can see in this image, that the breadcrumb trail is following in the direction which astronaut is supposed to follow. Now, so our goal is to have a path ready for the astronaut that is shortest, avoids obstacles, and is easier to follow. So in this example that you can see, the path represented by the colored balls, it avoids the hills and the craters to reach to the destination. The another thing that you must mention that must be that the golden mesh, that is the recast graph that is generated and utilized by the A star algorithm. So this is generated on a customized digital terrain model that we mapped out for the rock yard. So yeah, other than that, we are like our Pathfinder have customizable heuristics based on astronaut vitals, such as oxygen levels, suit pressure, suit battery, which can help make a path tailored to each astronaut. Now, other than Pathfinder, we have other implementations in a navigation system that helps make it more better. For example, the real-time terrain analysis. So basically, the ability to demarcate walkable and non-walkable regions with green circles and red crosses in like a real-time 5-meter, 42-degree close range in front of the astronaut provides uh, great information for short-range navigation. We also provide the astronaut with the ability to change all these settings, configurations. For example, the transparency of the markers, the number of the markers, and the areas covered. We also have the ability to generate a point of interest on the 3D mini-map on the HoloLens. You can do that by pinching on the HoloLens or even amazingly with your gaze, powered by our AI system. Just looking at the map and there you go. Now you see that the second orange marker is displayed in the real world view based on calibration and converting the coordinate system to the real world.
Our focus for our UI design this year is to create a user interface that is as intuitive and non-obstructive as possible. We understand that the limitations of the HoloLens field of view constrains any hologram placements to a small 42-degree box in front of the user, as well as the importance of having much, much greater situational awareness in high-risk environments such as space. As so, our solution is to create a hand-based UI that does not obstruct the user's field of view if it is not currently in use. You can simply open it by looking at your palm and close it by releasing. Finally, pop-out panels can actually display complex information such as telemetry readouts and spectroscopy, and can be deployed on demand from your hand menus. And if you would like to view multiple panels at once, we do have a dynamic arrangement manager that can arrange the pop-out panels to optimize the visibility of each panel, considering the constraints of the HoloLens 2. As for future work, we are looking into methods of calibrating the user's orientation without the use of a compass, which, of course, on different planets that we may not have the ability to use a compass. Then we would like to shift our short-range markers away from using the red crosses and green circles into doing edge detection along edges, as currently our method only calculates the normal of the floor in front of the user. And we would like to account for contingencies, such as is this connection from the telemetry stream server or our AI server. Currently, we do have a pretty streamlined way of connecting with a holographic keyboard, and on top of that, a drop-down of last known connections. So we can easily facilitate that, but if we are able to actually automate the reconnection process, that would make that so much better. And finally, we'd like to conduct further usability study of computer vision for the UIA egress. So looking into different ways that CV can be used for doing sequential tasks, such as egress. Finally, I'd like to give a huge thanks to the team that made it all happen and our faculty members, Professor Barnhart and Professor Yang, as well as our mentors, Dr. Reisman and Tim from NASA.
Awesome job. Really cool video. And my first question is about your NLP system. What library are you using? And also, how is it off cloud?
It's completely running on a server. We built it from scratch, but it's based off different open source libraries. So including deep speech, Mozilla Deep Speech. We retrained actually a language model on USC supercomputer, like a tiny one, just to improve the accuracy on the commands that we write, which are about like 50 commands, but you can say them in whatever way as long as they mean the same thing. And text to speech is PyTCSX3, which is very straightforward actually implementation, and the RASA for intent handling also on our server, which is in theory could be deployed on the astronaut suit, just an embedding system. And at the end, the connection is through socket IO, and we get the raw stream of the microphone from the from like some binaries that are used by Microsoft.
Yeah, I was just wondering how you created the map, the gold grid of the area.
Yeah, so for the creation of the map, I can go over that process. Essentially, what we've done is we've ripped a DTM off of Google Earth through a pipeline from Google Earth into RenderDoc into Blender, and from there, post-process it, optimize it for Unity, import it, and then Supam, you can explain how we get the recap.
So once we get the DTM, we basically convert it into a navigation mesh. And so after we have the navigation mesh, we basically mark the areas that are traversable on the map or not. That's like the golden mesh you see. Like all the golden area is where an astronaut or a rover can go, has no obstacles, like or a rocket.
And the total size of the map is well under 100 megabytes.
So this map is dynamically generated. So for example, that you can change the map in real time. That's why like when we test on HoloLens, it takes like 30 seconds because of the computation. And also for the waypoints, like for navigation, those are not pre-built. Like astronaut can point and like pinch any waypoint on the map in real time, and we'll have a path in like 30 seconds to that.
I have two questions. One of them is why did you select the colors you selected for the breadcrumbs for your navigation map?
We had actually the like solid green, but this is like the material that changes color based on the light. So if you see based on the light, it goes from like it has the entire gradient of rainbow. I love that material, so I just used it for development.
Fair. My second question is how robust is your terrain analysis tool and how did you train it and test it in different environments?
As for robustness, it relies on the spatial mesh that is generated by the HoloLens. So it is dependent upon light. That is the greatest dependency. We did create a pretty robust lighting vest, which our testers remarked about almost as if they were not feeling anything. But in terms of the algorithm, so there is no training involved. It is simply casting raycasts and calculating the normal. So if the normals exceed a certain angle, then we can surmise that perhaps this is a rock, a boulder, or something that is not flat.
So you had a lot of features. I would ask is were you able to successfully ship every feature and demonstrate it in the Rockyard? And if not, why?
That is a great question. Integration is most certainly the biggest challenge that our team has come across. And in terms of integration, the all of the footage that you saw was on one single build, meaning all the features were integrated into one cohesive unit. So yes, we were able to generate, a short-range markers, long-range navigation, connect to the AI server. However, our greatest enemy, it seems, on the last test was the connection. So something that we had not predicted was perhaps walking too far from the last Wi-Fi access point, because the craters are actually a little bit further from the spectrometry site, which is where the second WAP is located. That might have actually resulted in some packet loss of transmitting, for example, AI commands back to the server for processing.
Thank you so much.